are we good to start?
Well, so let's mute everybody.
Can you hear me okay,
Yeah.
etc.? Okay, good.
You've done your slides in LaTeX. Wow.
Yeah. It's just it was just a pain to typeset it in a different thing and then bring it back. And I mean, of course, I worked a lot by hand mostly. So this is obviously translated uh, a bunch from different versions. And I just want to acknowledge that this was a really special gathering of people, and I feel really humbled and grateful to be presenting this material today. And of course, I feel really upset that I'm also replacing another speaker, and I really apologize for that, but you know, somehow something worked out and I'm able to present this today. So
Chari will
I do
present
want
at the
to,
next opportunity. It'll be fine.
yeah, I will introduce myself at a different point, maybe if we exchange emails or something, because there's a bunch of stuff to go through today. So I'm just gonna jump right in. As,
Okay.
yeah.
I'm going to mute everybody else, so you'll be one of those people. So you'll just have to unmute when I do that now.
Okay.
So you're muted now, and then we're ready.
Okay.
Okay.
So you know, if you have a piece of paper and a pen, or you know, if you find something interesting to jot down, please feel free to do that and take screenshots or whatever. Um, and yeah, here we go. So before we even start, of course, you might have read the title of Appendix 9, which is a proof of Riemann's hypothesis via Denjoy's equivalent theorem. And this, we're gonna see what these things are before we even start Appendix 9. So on to the first statement, which I hope everyone can read okay. I tried to expand it a little bit so I could
Right. Can you
jump out
move
of
into presentation mode, Sahu? We don't need all the background stuff, just the main screen.
Yeah, I have a PDF version of it. If you prefer that, I could just go there.
Okay.
Yeah, and before we even do that, I just wanted to say that there are some sources that I'm citing here that are primary. So this is Edwards' Riemann zeta function. And essentially, we're going to look at this chapter here and talk a little bit about that. But we're going to go through Edwards' analysis of this paper, which is the original Riemann paper. But I'm preferring this translation for a reason, but Edwards has a translation of Riemann's paper as well at the end of his book. And I keep correlating the two, so it's fine. And this is Denjoy's original paper as well. So we're gonna quote that. And here, yeah. So I apologize for kind of a lot of stuff here, but I'm gonna expand this so you can read. Okay. Let's see. Full screen mode. Okay.
Lovely.
Better. So we were on this slide, and I'm just going to read it out. Riemann hypothesis is a conjecture first made by Riemann on the number of primes less than a given magnitude in 1859. And it's about the zeros of the zeta function, which you see here, whose domain is the complex numbers s and c, where s equals a plus bi. And many writers choose sigma for a and t for b, but we're just going to keep them a and b because you're going to basically learn the whole Greek alphabet by the end of this presentation. So anyway, this is zeta. And by convention of analytic continuation, which we'll see a little bit later, the trivial zeros of zeta are the integers -2, -4, -6, -8. And this, even though it's called trivial zero, it might not be very obvious why that's true. But by convention, those are the values that converge. And the remaining zeros of zeta are called the non-trivial zeros, which and Riemann's hypothesis, the conjecture that he made was not exactly stated in this way. This is the way that we have been seeing the problem for a while, which is that the non-trivial zeros of zeta are always going to have a equals half. And people see it geometrically, like the zeros lie on a straight line, etc. And this is the form that we're most used to this problem. So this identity is extremely important, and I feel like the whole presentation pretty much can be summarized into that. Like that is one of the most important relationships of zeta that is there. And here's a small derivation of this, which you can find in many books, like Weisdahl has a good account of it online and in his writing as well. But I'm not going to talk too much over this, but this was in 1737, and you can see how the primes are basically in a relationship with zeta. And we usually call this the Euler product, or the product formula for zeta, or many different references, but many different ways of referring to the same thing. But it's basically this 1 over 1 minus 1 over p to the s. Product of that. Like a sum is a product is a sum. That's all part of zeta. And okay, so we'll move to the next one just because there's a lot. Then we have the factorial function, which is notated capital pi, like big pi, due to Gauss. We usually say it's gamma. And I'm just going to use this notation because Riemann used it in the paper. So if anyone who's interested in reading the paper after the talk, they might have a better sense of how to navigate it. So essentially, it's like they're extending the factorial function to the real numbers. And, we're not going to derive this stuff now, but I'm just going to show you the historical, precedent to how Riemann came to his results and things. So we'll see that essentially Riemann quotes this, which we find aspects of it in these works. I'm not going to talk about it more, but I'm just going to say that this is like the form of zeta, that zeta can be expressed as this integral multiplied by this big pi or gamma factorial function. And Edwards has this analysis of this. Is according to Edwards, a contour integral above clearly converges for all values of s, real or complex, since e to the x grows faster than x to the s as x tends to infinity. Since the factorial function is an analytic function of the complex variable s, which has simple poles at -1, -2, -3. So gamma of minus, sorry, I used gamma, but this function will have poles at s equals 1, 2, 3. So we know zeta converges for 2, 3, 4 because it doesn't converge for 1, that's for sure. And the integral must have a 0, which cancels the pole at these places. And so this is like standard analytic, this is complex analysis, analytic continuation. And we're going to see how Spencer Brown is like totally different, but we're going to go there later. So we're going to go to the functional equation, which, and also if you read Riemann's paper, this is pretty much how it goes. Like he's referencing some things and he's moving really quickly and he jumps around once or twice. So I'm just following the timeline of reading his paper and Edwards's timeline as well of how Edwards presents the problem. So the functional equation basically is a really beautiful thing, and you'll see it's a Riemann continues that the relation between zeta of s and zeta of 1 minus s. So if you substitute when s is replaced by 1 minus s, the function remains unchanged. So that's the functional equation, and we'll see this in many different forms. But you basically, it's this substitution of this replacement of s by 1 minus s that gives this balance. So then Riemann introduces the xi function, which I'm just going to make a note here that Landau is the one who kind of corrected this, but this capital xi, I guess, of t, Riemann makes this substitution of half plus it, which is a little confusing because it kind of it gets confusing when you read the paper, like why did he do that at that point? But basically Edward says that Riemann makes this xi function, which basically he multiplies by this s times s minus 1 over 2, which already is very familiar object, but now we're in the complex domain and things aren't as we might have to not take things for granted in this domain. It's like, we might not even have definition of function, for example. You might have contradict things. Anyway, so this is the footnote on page 16, and this is the xi function, and xi is in a relationship with zeta. So Riemann basically starts studying the xi function because zeta is related to the primes by Euler, the product that we saw right in the beginning. So in the section of Edwards's book, the roots rho of xi, he gives a little more explanation here about basically that let me just read it out. So given a convergent infinite product can only be zero if one of its factors is zero. Zeta of s equals the product cannot have zeros for re s greater than 1, since xi of s equals this, and also since the other factors in this product only have the simple 0 at s equals 1. We know that none of the roots rho of 0 equals 0 lie in re s greater than 1. And since we know that rho and 1 minus rho by functional equation have so we know that none of the roots lie in this half plane as well. So if we know that it diverges above this, it diverges below that. So all roots lie in this strip, which is called the critical strip, or what people say. So the product representation of xi of s, basically Riemann for the next couple of steps in the paper comes at an identity that looks like this. And there's some explanation here. We don't really have to go into it because there are some bigger things we want to talk about. And also rho is multiple roots are counted multiplicity. So it's if you have the same root appearing multiple times, it's also counted. And you should notice that basically that's in a polynomial form, that Edwards is saying that, okay, polynomials can be expressed in this form. So xi of s is like a polynomial of infinite degree, because we know that there are infinite number of primes, which also the Euler product formula showed us that, because it's basically a bijection from natural numbers to primes. So also Edwards cites this series representation, which he prefers for xi of s, which is really beautiful. It's very clear too. It has a half in there, and it's kind of nice. It gives a good approximation of xi of s in any finite part of the plane. So we're gonna jump to the J function because that's pretty much what happens in Riemann's paper. Like, he jumps around, and you use this identity here, which it's kind of neat, and you can play with this and move it around, and he basically defines a new type of, like, this is the Stieltjes integral, which so he basically Edwards introduces the J function in this in this way, and he defines the function to be J. He's the one who named the function J. Actually, in the notes you read, he says it very distinctly that Riemann called this function in a very general way, which by f. And so to give it a little more importance, Edwards names it J. J for jump, probably. So this one is a kind of fun and easy way to know what J is basically begins at 0 for x equals 0 and increases by a jump of 1 whenever you get a prime. And jump of half for prime squares, jump of 1/3 for prime cubes, etc. You can read this in this section. Okay, so this is how Riemann introduces the J function in a very general way. So let big f of x be equal to the number when x is not exactly equal to a prime number, but let it be greater than half by half when x is a prime number, so that for any x at which there is a jump in value in f of x, this, which is really, it should remind you of, like, he's trying to do some limit here because it's in the neighborhood of x, etc. But so you can read, this is how Riemann introduces in a very general way. And we get the same yeah, so we should see Edwards comes back and shows us in the J notation that J is equal to pi of x plus half pi of x to the half plus 1/3 pi of x to the 1/3 plus dot 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 till x till infinity. And you should already notice that, hey, why is pi here? Why are you confusing me even more? I saw pi before in a different context. But yeah, I mean, like, mathematicians do that a lot. They just use the same symbol for many things. So this one, this is due to Landau and Handbuch, which is if I think it ought to be translated and available in more accessible format, but it's not. It hasn't been translated yet. Anyway, so this notation is used by Landau for the number of primes less than a given magnitude. If you remember, that's the title of Riemann's paper. And Edwards reasons that since in the same way the number of prime nth powers, p to the n less than x is pi of x to the 1/n, J can be formulated in terms of pi, and Mobius inversion gives us this. And Mobius inversion, it comes from Mobius in this paper in 1832. And it's given in this very general way, but which we'll see later when we go to Appendix 9. But what you need to remember from this is that J can be inverted to, and it spits out the Mobius the Mobius sign, like a minus, plus, etc. So it starts adding this coefficient of either a minus or
A
plus.
comment?
Yes.
You haven't defined the Mobius function yet, but you will. I just wanted to let people know that's an important function, and it will come up in a moment.
Yes. And so you see, you'll see that the zeta function is very related to the Mobius function. And we're interested in the prime numbers, and the prime numbers connect to zeta in the special way. And we went off to xi, and now we're at j, and we've got a mu. So the mu is connected to zeta in a very close way. So I don't want you to lose that track. Now we go back to Riemann gives a second proof of the functional equation, and I was reading that by Edwards was saying that possibly because the first one was the way he found out about it, I guess, and the second one was a little more rigorous. But basically in Riemann's paper, he's referencing Jacobi, and Edwards also talks about it a little bit. And for that context, we need to know that this function is now defined, this e to the minus n squared pi x, which in Riemann's paper is nn pi x. He writes it nn. He doesn't write n squared. And he makes that substitution early on too, so you'll see this is a familiar character. And this one, I'm really happy to find this source because I think it'd be important for someone who's trying to investigate this. This is a good, I was able to find it, trace it through Edwards sources and get this, which is this identity, which is attributed to Poisson by Jacobi. And essentially, once you see this identity, you'll start seeing what Riemann is doing, and his substitutions kind of start making some vague sense. Like, okay, this looks formally right. And so I'm just going to read this part. Since xi of x approaches 0 very rapidly as x tends to infinity, this shows in particular that this function is like this, which already people should get a little excited. That kind of looks like something that we want to talk about later. Anyway, that's a aside. But this is how Riemann writes it up here at the top. That's how he references Jacobi. So I just went there. Then this is page 4 of Riemann. This is kind of what he's doing here. I don't know if you want to get bothered by these symbols, but basically he comes to this, and the 1 over s times s minus 1 is basically what all of this is doing, showing that this is equal to 1 over s times s minus 1. And even though they look kind of complicated, you see it's really not that complicated. It looks like simple relationships coming from simple equations. And so this is a second proof of the functional equation. This also says that zeta is analytic, and oh sorry, we let me just read it. So since xi of x decreases more rapidly than any power of x as x tends to infinity, the integral in this formula converges for all of s. And that this gives, therefore, another formula for zeta of s, which is valid for all of s. And one note to make here is that Riemann's intention was to find a formula that's just valid for s. He didn't talk about analytic continuation or anything like that. That comes later, and there's Weierstrass and a whole rabbit hole there. Basically, we're looking for a valid formula. He's looking for a valid formula, and so this is another one. And it gives an alternate proof of the fact that zeta can be analytically continued. Since both sides of the equation are analytic, the equation holds for all s. And since this big monster is unchanged by s equals 1 minus s, this proves the functional equation of zeta, which is here, and xi. And xi and zeta are, of course, equivalent because of this. So we were talking about that series representation of xi. Here's the actual form of it. The a sub 2n coefficient is basically this. And Riemann said that this series, as an even function of s minus half, converges very rapidly. So a little more comments, like Edwards thought Riemann was a master of evaluating and estimating definite integrals. He was also a master of Fourier analysis, and his work must definitely be counted his greatest contributions to mathematics. Riemann applies Fourier inversion to this log zeta over s to get the j function. And the j function, of course, can be brought back into in terms of zeta, which is what Edwards talks about here, and he shows how why it's true for the real part being greater than 1. So this source also I went to here, and I would say paper 12 of Riemann's collected papers is really good. Also hasn't been translated yet, but again, it's you could navigate through it if you had to. So this one, for this series, a sub n and b sub n can be determined by this formula, and f is any arbitrary function. So this is a huge, and of course many fields of mathematics have been made out of this. And but this is the source. This is where what Riemann was referencing. What is Fourier's theorem? What he says Fourier's theorem in his paper. So yeah, I don't want to talk too much about this, but yeah, I already said earlier that Riemann substitutes s equals half plus it, and that's, I thought it was a bit premature. Edwards thought it was an error. No one's going to say it's an error, because I think, Riemann basically did what he did and found a truth that he saw and came back and, made the substitution, I guess, earlier on. So it's not a very serial reading of the paper, and the paper is not presented serially too, so it's tricky. And of course, in Riemann's paper, we get this vertical density of the roots of xi between 0 and t. The fact that the vertical density of the roots rho is in some sense a constant times log t over 2 pi was, according to Edwards, stated by Riemann without proof. So the proof was finally found by von Mangold in 1905 for that. And yeah, you're gonna see like this log. Why is the logarithm always there? And this is how Riemann had presented it originally on page 5, and I'm referencing Wilkins here. Yeah, we should read it. So the number of roots of xi of t, which you remember t, equals 0, whose real parts lie between 0 and big T, is approximately t over 2 pi log t over 2 pi minus t over 2 pi, because the integral d log zeta of t, taken in a positive sense, around the region consisting of the values of t whose imaginary parts lie between half I and minus half I, and whose real parts lie between 0 and t, is up to a fraction of the order of magnitude of the quantity 1 over t, equal to t log t over 2 pi minus t times I. This integral, however, is equal to the number of roots lying of this equation lying within this region multiplied by 2 pi I. One now finds indeed approximately this number of real roots within these limits, and it's very probable that all roots are real. According to Bombieri, the statement that all zeros of the function xi of t are real is the Riemann hypothesis. So this is the original statement. It's about xi. Riemann's conjecture was on xi, not on zeta. But we know of it as a thing of zeta. So now that we've gone all the way around to understanding what the Riemann hypothesis is and the conjectures of what it's about through one historical lens, we're gonna come back to it in different forms. So the prime number theorem, what it was called, was basically a conjecture that Gauss and Legendre made. Gauss apparently made it when he was 15 or something. I don't know. Like, I feel like if you had a table of values, which is what Apostel says, by examining large blocks of primes, one finds that their average distribution seems to be quite regular. And 1851, Chebyshev proved that if this ratio does tend to a limit, then it has to be 1. So, but that doesn't mean that the limit is 1. He proved that if it does go to a limit, then it goes to 1. So finally, this was proved by Hadamard and C.J. de la Vallée-Poussin. I don't know how to pronounce that, so please don't make me do it again. And it's this. So it's pi of x, which is the number of primes, and x over log x. At infinity, they basically behave in a similar way. And you can see some people have suggested, okay, prime number theorem is this, but you'd see that x over log x, although it is a good estimate to the number of primes, it's not one of the better ones. There are other estimates, and like lie x, etc., and or even 1 over log x, which Spencer Brown is a proponent of that one. And Hardy, this quote I feel like is kind of important to know, and because it's kind of talks about the entire talk up until now. So Hardy was known to have addressed the Mathematical Society of Copenhagen in 1921, ruling out the possibility of an elementary proof, which basically means not using complex analysis and or extremely weird techniques, of the prime number theorem, asserting that some theorems lie deep and others nearer to the surface, and that if anyone produces an elementary proof of the prime number theorem, he will show that these views are wrong, and that the subject does not hang together in the way we have supposed, and that it is time for the books to be cast aside and for the theory to be rewritten, which I feel like is a very epic thing for Hardy to say. But basically, Selberg found an elementary proof years later, and that's kind of embarrassing for Hardy, but this happened. And Erdős attended the lecture that Selberg was giving on his findings, and basically Erdős had a conversation with Selberg outside in the hallway, and saying, hey, I think that there's a way that you can do this. And so there's a story there, and
should be understood that it's they both proved it.
They both proved
I mean,
it.
it wasn't that Erdős attended a lecture in which Selberg proved it.
Okay.
Erdős talked to Selberg, and they got an idea between them that led to the proof.
Yeah, but it's sad that
They split. Then they
the
split.
miscommunication between them, perhaps something happened and the politics are surrounding it, and also how you see how sensationalized everything is becoming. So, that unfortunately damaged the relationship between Selberg and Erdos, but they found these quote unquote elementary proofs without using zeta or complex function theory, which leads us to question what exactly is, anyway, there's big questions here. So we go to Landau's handbook because Hardy basically said that this is the first time the analytic theory of numbers is presented not as a collection of few beautiful scattered theorems, but as a systematic science. So if you open this book, which I've already said that someone needs to translate this quickly or soon, but basically if you open the book, you'll see the first couple of pages starts with mu and lambda. You saw mu earlier, and lambda is going to be defined again, very soon. So this slide is a bit dense, but it has a lot of important information that's going to show up in the rest of the talk. So mu of n is defined as -1 to the k if n is the product of k distinct primes and 0 otherwise. So stop right there. And basically, if you have a piece of paper, write mu equals either -1 or +1 or 0. And mu of n is 0 if you break n up into its prime factors and any of the factors has a higher degree, like if you have 2 squared times 3 or 3 cubed times 7 or something, those numbers are all going to map to 0. Their Mobius value is going to go to 0. So we're only going to look at numbers that are made out of primes, but the primes are only counted once. They're only multiplied once. They're not, you don't count numbers that have multiple primes in their prime factors. So those numbers, if you have an even number of prime factors, then you get +1 of Mobius of mu. And if you have an odd number of prime factors, you have -1. That's basically what mu is. -1 to the k, where k is the number of primes that it's made up of. And the Liouville function is in a way an extension of mu, if you think about it this way, that now you're incorporating multiplicity as well. So, if you have 2 squared times 3, you have 2 times 2 times 3, that has 3 parts, and that's odd. And so lambda is going to be -1. So lambda's, if you have the paper, just write lambda maps to only -1 and +1. And this is how they're related to zeta, and zeta is connected to the primes. So Landau starts with mu and lambda, and this you can see in Titchmarsh. These are the equations where he mentions them, and there are other references here as well for that. So basically this is important. You see that 1 over zeta, like the inverse of zeta, if you remember the J function when it was inverted, we got the Mobius function there. So it's the inverse of zeta gives mu of n times n to the s, which we had seen earlier there. Okay, so without wasting any time, I guess, the Riemann hypothesis and Mobius mu are connected in a very simple way. So in chapter 3, averages of arithmetical functions, introduction to analytic number theory, Apostle says the statement mu of n has average order 0, i.e. mu of n over n, as n turns to infinity, the sum converges and has sum 0. That is equivalent to the prime number theorem PNT. And as referenced by Spencer Brown in Appendix 9, by Edwards in section 12.3, by Apostle and by Derbyshire, RH is equivalent to m of x equals big O of x to the half plus epsilon, where m of x is the sum of Mobius values up until with n less than equal to x. And this is we say f is big O of g of x, if there are positive constants c and x naught such that the absolute value of f of x is less than equal to c times g of x whenever x greater than x0. It's kind of complicated, but what you want to know is like limit of this these two at infinity are basically asymptotically equal. That's what they say. And we'll come to the bigger, broader definition of big O later. But for now, just keep this in mind because this is what Spencer Brown uses, essentially. And RH and lambda also have their own thing. So, and this is basically, if you read Landau's dissertation, that's pretty much what it's about. Landau does his whole thing on lambda. And I think Borwine's the Riemann hypothesis 2008 has a lot of stuff on lambda if people are interested in lambda. And PNT is the same thing as the previous slide, mu of 1 plus mu of 2, blah, blah, the average of that equals 0 is PNT, and the same thing for lambda. And as referenced by Spencer Brown on page 209, and Borwine, RH is equivalent to this. Where's the n to the half plus epsilon? Basically, it's to the half plus epsilon. N to the half plus epsilon is in some way very closely equivalent, basically, to the Riemann hypothesis. So in the growth of m of x, Edwards, Stieltjes measure, etc., you have another way of looking at m of x, and I'd say it's worth reading if you ever get a chance to go to this chapter. And he basically comes to this that, you know, m of x does not grow less rapidly than x to the a for any 8 less than half. Cool. And this one, again, just to reiterate that the Riemann hypothesis is equivalent to this statement here. If you prefer to read it in these hieroglyphics that we are so used to reading, it's over here. And if you prefer text, there's here, Edwards talks in this way. So this is page 260 to 261, section 12.1. And basically Littlewood is the one who proved that this sufficient condition for the Riemann hypothesis is also necessary, hence proving that the Riemann hypothesis is equivalent. So he showed not only that it's sufficient, but also it's necessary, and that's why we are here. That for every epsilon greater than 0, the function m of x, which is the sum of Mobius values over x to the half plus epsilon, approaches 0 as x tends to infinity. On page 268, Edwards basically, this is what I had shown in the beginning of the talk, the chapter that it was on, the PDF. And this is it's in a chapter called Miscellany of Edwards, like miscellaneous topics, and it's chapter 12. And in this, I'm just basically quoting him, and I think this is worth reading. So let me just read this. So suppose an unbiased coin is flipped a large number of times, say n times, big N times. By the Moivre-Laplace theorem, the probability that the number of heads deviates by less than kn to the half from the expected number of half n is nearly equal to that integral e to the minus pi x squared dx. So you should see that form of the n squared pi e to the n squared pi, the substitution that we had seen earlier, in the sense that the limit of these probabilities as n tends to infinity, the limit of the probability of what? The probability that the number of heads deviates by less than kn to the half from the expected number of half n. So the deviation from half n is nearly equal is nearly equal to this function, the integral, in the sense that the limit of these probabilities as n tends to infinity is equal to this integral. Thus, if the total number of heads is subtracted from the total number of tails, the probability that the resulting number is less than 2kn to the half in absolute values is nearly equal to this. The fact that this approaches 1 as n tends to infinity can be regarded as saying that with probability 1, the number of heads minus the number of tails grows less rapidly than big N to the half plus epsilon. So of course, there's just before we get too excited, etc., you have to see how he sets up the story. And it says, like, suppose an unbiased coin is flipped a large number of times, and it's making assumptions. Okay, like, if you had the piece of paper where it says mu equals either -1 or 1 or 0, and lambda equals -1 or 1, you could think, okay, like, imagine mu is like flipping a coin. So if I get heads, it's +1. If I get tails, it's -1. And that is plausible. It gives, and if you go to that appendix, Edwards says it does give a fleeting glimpse of plausibility of RH. That's how he had stated it. And if we continue on page 268, he goes a little bit further, and he says if we consider a very large square free integer n, and square free integer, remember, square free integer meaning it doesn't have any you break up the integer into its prime components. It doesn't have any prime numbers that have powers greater than 1. That's what square free means. It has no squares. So square free integer n, you imagine that n is going to infinity, basically what he's saying. So imagine it's a really large thing. Then mu of n equals either plus or -1. But then the evaluation of big M of x, which is the sum of mu, would be like flipping a coin once for each square free integer less than x, subtracting the number of heads from the number of tails. It was shown above that for any given epsilon greater than 0, the outcome of this experiment for large number of flips, that is, the number of flips goes to infinity as x tends to infinity, because among other reasons, blah, blah, blah. That's his footnote. So for a large number of flips is with probability nearly 1, less than the number of flips raised to the power half plus epsilon, and a fortiori less than x to the half plus epsilon. And this is Denjoy's original reference in French, and I translated later, and actually it's interesting to see this, but we're going to come back to it very soon. And Edwards, however, goes on to write that it's perhaps plausible to say that successive evaluations of mu of n equals plus or minus 1 are independent, since knowing the value of mu of n for one n would not seem to give any information about its values for other values of n. And this is the part which is tricky, because it came from the coin unbiased assumption that the coin is the determination of what value the coin is showing is unbiased, and that assumption was incorrect. And so Spencer Brown, as we will see, and it's an analogy, of course, I don't know how serious Edwards was being, because I don't know if he really read Denjoy's paper in a more general way. But anyway, so Spencer Brown says that it's that in Appendix 9 you'll see how mu of n is in a very, very specific relation to itself, and that it doesn't make sense for us to assume that mu is random or independent, because it's not.
One more comment. This idea was that if mu of n was sufficiently like a random variable, then you would get the Riemann hypothesis.
Yes.
No one claims that it is random, and even Edwards doesn't claim that. But the question is, what's going on? Because after all, it looks like that would be related to a random variable, but it isn't.
Mm-hmm. And I think this slide kind of talks about it a little bit, that it's given that there's experimental verification if we try to do it with a real coin or something, but it's not, it doesn't, I don't know if we should take it seriously or really address it, but we should at least get the story straight that mu is not random, and that the successive evaluations of mu are not independent from one another, as even if it is stated here and Edwards is the one who wrote it. I think we should be very careful. Okay, so now we're ready to go to Appendix 9, now that we have a little bit of historical sense to go into the problem. And the appendix starts with this description of the proof. That the Riemann hypothesis is true if and only if the number of positive and negative signs of mu of n are asymptotically equal remember what asymptotically equal means. So let's see that f of x sim g of x relation for two functions f comma g from R to R means that this limit of f of x over g of x as x tends to infinity equals 1. This is the simplest definition. This is the same thing as saying the big O notation. Under these conditions, the two functions are said to be asymptotically equivalent or simply asymptotic. Referencing then, okay, so let's go back here. If and only if the number of positive and negative signs of mu of n are asymptotically equal, referencing Denjoy's probabilistic interpretation, which is this paper, that RH is equivalent to the proposition that any square-free number taken at random has an equal probability of containing an odd or an even number of different prime divisors. Page 203.
I'd better make another comment at this point,
Yeah.
so people don't get a wrong impression.
Yes.
We do not yet see to what extent Spencer Brown has a proof here. Also, Spencer Brown speaks in obscure ways from time to time, such as this paragraph, which, if you interpret it literally, is wrong. It's not enough that it's just asymptotically equal. That would be the prime number theorem, not the Riemann hypothesis. Nevertheless, as we go along here, you're going to see some very interesting ideas which are deeper than these sort of strange misstatements that occur from time to time.
Thank you, Lou. That is very important to keep in mind. And it's been tricky. That's how it's been very tricky to get this. How do I get the story straight? And his historical evidence and what he's referencing, and yeah. Anyway, so we're gonna move forward and just look at the zeta of 2s over s in Denjoy's in Denjoy's paper, which is basically the Liouville. If you remember, the lambda function is related in this way. So he was looking at lambda. Okay, so the appendix 9 highlights this recursive formula, which is very, very important, and I think it's worth writing down if you have a piece of paper, that the number of primes, which is pi of n, the number of primes less than n, is equal to the number of primes less than square root of n plus this sum of mu of d times n over d. And n over d is the floor of n over d. So, you're not, whatever's the quotient that you get, not the remainder. So you just take the quotient plus, and also for each divisor, you take their Mobius sign, which is either minus or plus. So this quotient, when you add these, and this is not a regular sum, so I need to point this out, that the square root of n, it's not 1 to square root of n exactly. What we're doing is we are taking the primes, the first square root of n primes, essentially, or all of the primes that are under square root of n. I'm sorry, I made a mistake here. So all of the primes that are under square root of n, you collect those in a set. Let's say this is a set, and you start combining them. So you take the single primes and you take the doubles, you take the triples, etc. All of these, you make the sum for that. And I'll show you with some concrete examples how this works and why this works. And that this is basically an Eratosthenes sieve. There's nothing new happening here. So in the example, I chose 20. So pi of 20 equals pi of square root of 20 plus d equals 1 to square root of 20. Mu of d, 20 over d. And first things first, we're gonna talk about d equals 1 to square root of 20. What does this mean? What am I summing here? Square root of 20 is basically, just think about it like whole numbers. So square root of 20 is going to be 4. And what are the number of primes up till 4? It's 2 and 3. Okay, so now in this setting here, my set is 2 and 3. only 2 and 3. So I have the product, the primes, the collection is only 2 and 3. And so I form all the combinations of 2 and 3. So I have 2, 3, and 2.3. And those are the only terms that I need to do for this exercise. And you see how this works. Now what Spencer Brown does is for d equals 1, he rectifies the numerator by 1. So it becomes 20 minus 1. And I point this out over here as well. So specifically for d equals 1, Spencer Brown rectifies this to n minus 1 over d. Okay. And you can try this for any number. I've tried it for really, really large numbers, and it still works, and it's fun, kind of, if you're crazy. The next slide, we're gonna go to page 203. So the formula only uses primes up to square root of n, what Spencer Brown calls small primes, to sieve the remaining primes up to n, what Spencer Brown calls the large primes. And he says the Legendre-Spencer-Brown formula can be tested for any n, and the formula works correctly because its summation term yields the number of numbers less than equal to n that are not struck out by the Eratosthenes procedure of striking out those of them that are divisible by a prime q that is small in relation to n, that is within the square root of n rate, that q is in square root of n. In every application of the Legendre procedure, the small primes, that is the primes up to the square root of n, are needed to count the large primes as primes up to n. So remember, it's pi of n is connected to itself and pi of square root of n. And that can be recursed, etc. So two things to note, very important, that n over d, the floor of n over d is going to give you 0 when d becomes bigger than n. So if you have some n and you have d that becomes much bigger, and you remember that you're making these divisors by combining primes together and basically collecting them. So of course you're gonna maybe you're gonna make a product that exceeds n. So that is gonna give you straight up 0, and we know that. Now the second thing to note is that at n over 2, at half n, d basically crosses the half line of n, and the quotient gives you a 1. This is a very important property, basically, because this mu of d times floor of n over d is equal to mu of d in this section, in the lower section, what he calls upper and lower. So it's a little bit of a cognitive dissonance type thing, maybe for some people, but he calls this one upper and this one lower.
Sahu,
Yes, hi.
I'm sorry, I just had a
Sydney.
quick question. Was that related to the critical region where you were talking about that critical strip?
Yeah, we're gonna come back to that specifically in a bit. But this one is we're still basically just working with natural numbers right now. It's just n, and we're
Okay.
just counting the number of primes, and this simple formula where pi of n, which is number of primes, is related to pi of square root of n. So if you feed it, if you only need square root of n input to generate n, the information about n primes. So
Let me make another comment. Sydney, yeah, we keep seeing that kind of relationship. Like it looks like, oh, this one half ought to be related to the other one half.
yeah.
But they're quite distant in the mathematical story that we're telling. Nevertheless, we feel like there's something going on there.
Yeah. Thanks for the question, and please, if anyone wants to ask something in the middle, please go ahead. So anyway, so this n over 2 relationship is very important, and we're gonna see some reasons why this happens. And let's just read here. On page 205, Spencer Brown says, in the lower section, the sum of the terms is exactly the sum of mu of d, because mu of d, n over d becomes mu of d here. So this is exactly the sum of mu of d. Call a series of such term an LSB series. This is Legendre-Spencer-Brown series. It says on page 205. Now, this one is very interesting. Jim had passed this along to me. It's a couple of slides from Vivek Dhan's notes for this class that Vivek offers. And it begins by defining div of n, which is the set of divisors that divide n. And formally, that means that dq equals n, that there exists a q in Z plus, and this q is unique such that dq equals n. He then considers identity maps of div n to div n, namely the map d to n over d, as a mapping of its own inverse, which necessarily gives you a bijection. So in this, you'll see this form here, which is kind of interesting and weird, that this can go to that can come back, and maybe it will be helpful for people in the future, or I don't know. Anyway, so here is another extremely important thing that I wanted to share today. This is how Spencer-Brown defines the function f of d, which is his LSB series. And this equals n minus 1 plus d equals 2 to n minus 1 mu of d n over d floor. And of course, if we adopt the same convention that we have been adopting.
You mean f of n?
F of n, yes, sorry. This one. Let me make a note of that here. F of n. Yeah. No. So I'll tell you why I used f of d here. But yes, I can see why I made a mistake there. But what I wanted to say was that this n minus 1 here is the same rectification thing that he was doing in the prime counting function pi. So I chose to consolidate the notation and just say d equals 1 to n minus 1, 1 to n minus 1. Given we know that for d equals 1, that numerator becomes n minus 1, and everything will be fine, and we can use this formula and remember it easier. So in Jim's conversations with GSB, during which actually Spencer-Brown wrote this appendix, and a lot of what Spencer-Brown had written came out of conversations with Jim and recommendations and suggestions. So this formula was written by Jim at this date, and so essentially, given this, what we have written here, we see this form of the formula in Jim's letter. And this is the one that we are going to use to compute Mobius values, and it's easiest for me to illustrate the what Spencer-Brown is doing using this, that you basically mu of n equals d equals 1 to n minus 1 of mu of d times floor of n over d, and it's the sign flipped. So the sum up until n minus 1 flipped gives you mu of n. That's basically what you want to take from this slide, and it's going to come later in many, many different forms. And Spencer-Brown himself also points at it in his cascade. So this is the one that I had prepared for us to see, because this is what made it easier for me to know what Spencer-Brown was doing, so I'm just sharing that. So as mentioned by Spencer-Brown, from our knowledge that mu of 1 equals plus 1, because 1 has 0 prime divisors and 0 is an even number, we proceed to discover mu of n for every subsequent number n without having to factorize any such n. And most practice, you start with mu of 1 equals 1, and then everything follows from there, because we know that mu of 2 is related to all of the Mobius values up to 2 minus 1, which is 1. And we know at d equals 1, that's rectified, the n minus 1. So mu of 1 times 2 minus 1 over 1 is just is just plus 1 inside these parentheses. Minus is outside, flipped, gives minus 1. Now mu of 3 is the same thing. You go all the way up to from mu of 1 all the way to n minus 1. 3 minus 1 is 2. So mu of 1 times rectified n over d, n minus 1 over d, sorry, plus mu of 2 times 3 over 2. And you can count it and see that it gives you, basically this formula works. And I just went up to 6, and in the paper we go up to slightly higher. We can. Yeah, if you have any questions so far, this one is an important thing to see what is going on. And this basically is the reason why what Edwards had said was not correct in that context. Uh, so
Yeah,
So is that
yes,
if there's one thing you want to take away from this, it's this formula
it's
about
basically
mu,
this.
because it just
Yeah.
shows really clearly that mu is not at all random.
And so it's not independent. It's against what Edwards was saying about being independent.
Yeah, so if we are doing a coin experiment with this, we cannot assume that this coin is unbiased. And
Okay.
that's how he started off his spiel. He was like, imagine we have an unbiased coin. So what if we have a different type of coin? You know, it still has two values, but it's related in this way. Maybe it could be different. No conclusions yet, but this is what it is. So if you see this, it's good. If you want to try a couple of examples yourself, please do. Um, if you want me to go back to a slide, I can show you the formula again, etc. I can do that. And I'm just going to go to what he's notationally doing because it's important. He does not specify these columns and what they mean and stuff. So I just want to clear / debunk that, or you know, if you're studying this material, I don't want you to be stuck on it. So I'm helping with the labels of these columns here. If you go to 215 to 216 on in the book, of course the first column is just D, which is the square free divisors, because you know that the non-square free, like a number like 4 is just going to give you 0, so you know you don't need it. So he also omits it. And of course we're going to start with 1 because we know that we're going to get the n-1 rectification, which will help balance everything off and give you 0. So some things to note about this already is that the sum of f of d equals 0 at the end. For all of them, you're going to see it's equal to 0. The sum of f of d here also 0, here also 0. And this is the one that he's presented in Appendix 9. Another thing you should note is this penultimate term in this column. If you flip the sign, you're going to get mu of n. You see? So the +1 here, when it's flipped, is going to give you -1. This one is just 0, so it's the same. This +1 gets flipped to -1. The penultimate term of this column, when flipped, gives you this mu for this row. -1 flipped to +1. And he points this out later too. It's a very important takeaway from this particular version, this cascade that he's doing on these pages. Okay, so then we go to another document that we received from Moshe. There was a letter that Spencer Brown wrote to him, and you know, we can spend some time reading it and stuff, but basically this is like the definition of of mu in a way. Like, you know, if you multiply, if you take the minus in, you get n - 1 plus sum d equals 2 to n - 1 mu of d n over d. So it's basically the definition of mu. But it looks pretty. Like the cascade that's in the letter looks really nice, and basically he kind of corrects it in a way again, and in which this column just spits out mu very naturally and nicely. So the last element on this list gives you the mu for, so mu of 2 equals -1, mu of 3 equals -1, 4 equals 0. And they look kind of nice and it's very compact, but you know, if you don't know what is going on, it's really hard to tell what exactly he's doing here. Yeah, I would say both of these cascades are important because on page 217, okay, so this is an important takeaway here. You can see the penultimate term in sum f of d, which is the third column in his cascade, with the reverse sign is the mu of d. That's the feedback. So on page 217, Spencer Brown says all the cascade requires is what previous cascades have told it. We also see that there is no need to list the final term for any n. So you don't have to write the final term because since the answer must be the penultimate term in the running total, which is the sum f of d, the third column, with the sign reversed. And so for the cascade we see on 215 to 217, the final term of sum f of d equals 0, which is what in a way he uses to sort of show that the summatory Mobius kind of is only moving -1 or +1, because this last step is actually splitting the Mobius value, which is just +1 or -1, so it's kind of wavering from 0. For Spencer-Brown's cascade in Letter to Moshe, the final term of sum f of d is mu of d, and we see that we see that how he kind of almost rewires this algorithm to spit out mu of x at the end, and it requires less marks on the page. It looks kind of nice. Anyway, so in general, for both variations of Spencer-Brown's cascades, we have this penultimate term with reverse sign thing, which yeah, which we can see here. It let's see, where are we? Okay, so I want to make sure we get through. Sorry. So this one is in his basically in his description of the proof, not in the description of the proof. He in his summary, he has the summary with 5 points where he says number 1, number 2, number 3. Number 1 basically is the one that Lou said was, you know, we don't know what he means by asymptotic, and if that's enough. But number 2 is I rectify Legendre's method of counting large primes in n and then corrupt it to give the answer 0 for all n. And 3, I split the rectified sum into 2 sections, upper and lower, so that the lower section eventually includes all values of mu of d, which we know, for square free d greater than 1. And this you can see is kind of simple. So the f of d terms, if you're summing from 1 to n, it's basically d equals 1 to n minus 1 plus the nth one. And we know the nth one is basically mu of n. And so this is 0. Basically, this is kind of saying nothing in a way, but also it's what he uses. He doesn't explicitly state it, but this is what it looks like. And any difference between the upper and lower sections can be seen to be self-annihilating because of the negative feedback between the 2 sections. Page 206. I'm just quoting him here. Okay, so this is what he does. He says by using the base case of n equals 20 and doubling n is 20. 20 is, what is 20? 20 is 2 squared times 5 squared. It gives you a mu of 0 because it has a square. And doubling n to 2n equals 40, then doubling 2n to 4n equals 80, etc. He keeps doubling. The average algebraic sum is the sum divided by the number of LSB terms displayed in each section, varies around and is asymptotic to 0. Since the LSB series or Spencer-Brown's cascade establishes a negative feedback relation between f of d and some f of d columns to yield the valid formula, mu of n equals minus penultimate. If mu of n is the nth term of f of d and mu of n equals f of n equals plus or minus 1, then the n minus 1th term of some f of d equals minus or plus 1 for square free n. That's basically what it's saying. So then Spencer-Brown kind of says that, you know, for any square free number such as n equals 2, since the final f of d term f of n equals mu of n equals 0, if we use the cascading algorithm in appendix 9, sum, sorry, it should have been sum. Also, since 5, as n tends to infinity, the lower section eventually includes the values of mu of d for all square free d greater than 1. This gives n from d equals 1, f of d equals 0 to, he kind of pushes that for larger and larger. And for any finite n, we know the partition of f of d into upper and lower sections at d equals n over 2, emphasize bijection d to n over d. When sum f of d from 1 to n is equal to 0, this means that the upper and lower f of d section necessarily cancel each other out and give 0, since every d is accounted for with its inverse n over d. This is Denjoy's original paper. We find that statement again, and I'm going to show the translation of it. So Denjoy starts there with mu of 1 equals 1, setting delta of n equals this function, which in Spencer-Brown territory is a negative penultimate f of d. And that this is true once you set delta of n. It is sufficient to show that limit 1 over log n equals half, it being impossible that the inequality less than half for the Riemann hypothesis to be justified. Yeah, this is, I wish that I had read this before, but this has been like very recent too. We finally managed to get the paper and the original paper, and so this is what it looks like, the original statement by Denjoy. And there are some other sections from the paper that I wanted to share here that that he says probability that the imaginary zeros of zeta of s lie on the right of sigma equals half, and that they're all simple is equal to 1. The less precise limitation, if epsilon is within 0 and 1, the probability that the absolute value of delta n less than 2n 1 plus epsilon to the 1 plus epsilon, the square root of that is inferior to n. And I don't know, like this translation also is, it requires some work, but I just wanted to share this. Some more comments from Denjoy, since we don't really read him directly that much, and since we're only working off of what Edwards has to say about one particular reading that Edwards has of Denjoy, so I thought it was important to just go straight to Denjoy and see what he's saying. Okay, so Legendre formula pi of n recursively relates to pi of root n via this sum, is rectified by sorry, some of these haven't typeset properly, so I apologize. But it's rectified by Spencer-Brown to yield the formula mu of n equals minus f of d, where f of d equals 1 to n minus 1 mu of dn over d. The negative feedback ensures this is 0. Though Edwards' analogy of coin tossing provides a glimpse of plausibility of RH, Denjoy's equivalent theorem does not demand that mu be unbiased. So, you know, even if we are using an analogy of coin tossing, I think the fact that mu is biased in a particular way is important to factor in if someone needs to make an argument. So the negative feedback property of mu n is used by Spencer-Brown to argue that the cumulative Mobius function varies around 0 and that its asymptotics are sufficient by Denjoy's interpretation to prove Riemann. Okay. So that's the end of Appendix 9. Appendix 0, I'm just going to fly through because I want us to have time to do a Q&A.
So
Okay.
let's make one comment here. Go back a slide.
Yeah.
The punchline is the last 3 lines on this slide.
Mhm.
That you have the Spencer-Brown's rewrite of the Legendre formula sets it equal to 0, and that means that half of that sum is just a Mobius sum. The other half of the sum is the sum of Mobius times floors. And Spencer-Brown claims that the balance that makes that 0 is, or can be thought of as a feedback, and is sufficient to show that the actual Mobius sums are very tightly asymptotic to 0. And very tightly means that they would satisfy the right inequality that we quoted earlier about the square root.
Yeah.
He claims it without proof, but leaves you with that feedback and Legendre formula to explore. So that's the crux of the matter. One can go on and really look at that, and you don't even need the analytic background. It's strictly, a strictly pure number theory.
And so transitioning in from there, it really was a matter of sitting with a piece of paper and actually working with the divisors. And I want to see if I can zoom in a little more. So I basically sat down and started writing primes, collecting their products, and the triples and the quadruples, etc. and you can start seeing that this collection that the one p sub I, p sub I dot p sub j, p sub I dot p sub j dot p sub k, triples, doubles, singles, and it's just one. These are all the square free numbers that that there are. Starting, if you start with a set of primes, you can form all of them and collect all of them in this really uh, simple way. And actually, I'd seen Lou had done this once when he shared his screen and we were looking at the Legendre formula. And this is a way that Lou had written out the factors. And so I started, doing it in the same way and working through it with larger sets. And what I noticed was you get the Pascal's triangle from this. It's entirely in the square free numbers. Basically, if you start with a finite set of primes, which is here, 2, 3, 5, 7, 11. I have 5 of them, and I just keep it to these primes. I'm not going to include anything else, and they don't even have to be in order. You can just have primes, any set of primes. You can make this collection just by combining them in unique way. And this is a partial ordering too, so there's one way of doing it and one way of enumerating it. This way it's easier. So the first discovery was that they correspond to the Pascal triangles. It's not a real discovery, maybe, because some people might have seen that in different forms and in formal symbolic way. But I just was counting with a piece of paper and pen. So I saw this and I saw some very special relationships here. So this is the Pascal triangle 1, 1, 1, 1, 1. These are the set of primes. And if you connect them together, you get the second row of the Pascal numbers 1 plus 2 plus 3 plus 4 plus 5 plus 6. So these are all of the possible products of this. And those are the number of divisors in pi dot pj, the doubles. In column number 3, which is the third column of the Pascal triangle, get the triples. In column number 4 is the quadruples, etc. And this is how Pascal had arranged the Pascal triangle originally, and he referenced something called the hockey stick pattern, which, if you notice, see the number 15 here is equal to the previous column 1 plus 2 plus 3 plus 4 plus 5, all the way up till here is 15. So all the way 1 plus 3 plus 6 plus 10, all the way up to here is 20. This hockey stick kind of looks like a Spencer Brown mark in a way too. I didn't realize. But yeah, so now you can basically see what we're going to do. This is a set of primes. This is the doubles. These are the triples. These are quadruples. The singles give you a Mobius value of what? -1. The doubles give you Mobius of +1. Triples give you Mobius value of -1. Quadruples give you +1, -1, +1, -1. So given the hockey stick identity, you have 15 plus here, and all of these are also 15 minus. So these cancel each other out. 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 Finally, these cancel each other out. And this one, the last one, 6 cancels 6 of these, and you're left with 1 prime. Is number 2. And that gives you a Mobius value of -1. And the number which we did not include is number 1, which is 1 is not a prime. It's not put in this column. And these are only the primes. So 1 gives you a Mobius value of +1, and 2 gives you a Mobius -1. So the whole sum is going to give you a 0. And this is the theorem. So let P1, P2, P3 all the way P root n. This is the first time I wrote it, so be kind. I have another version of this theorem as well. So let D be a member of this collection, all of the square free numbers, where Pi basically means P is a prime and I is in between root n, because I chose root n as the bound for this one. Pi dot pj is the doubles such that I less than j, and triples such that I less than j less than k. And if you sum all of these together, you get 0, big old 0. You saw with the Pascal triangle, it's the alternate sign summation. And this is the same theorem, but generalized to n. Proof. So we see how any collection of n primes can form divisors in P in this set, and that the number of these correspond exactly to the columns or rows of Pascal's triangle. The alternating sums of columns or rows in Pascal's triangle gives you 1, 0. So if you remember, the hockey stick pattern canceled everything till the last column. The first column gave you a 1. That's where that 1 comes from. So the total Mobius sum is going to give you -1 because that first column was the set of primes, which give you Mobius -1. So since mu of 1 is +1, the whole thing, the whole sum is equal to mu of 1, and that -1 comes from the Pascal triangle equals 0. Cool. So this one is just a quick slide. As the number of primes, that's n, tends to infinity, Pi eventually becomes a set of all prime numbers. Similarly, number of Pi.Pj will grow larger and larger till Pi.Pj becomes a set of all possible products of 2 distinct primes.
Sahu,
Then yes.
you're not proving that M of n is asymptotic to the sum over the divisors.
Yeah, I don't know if I'm proving it.
No, you're not. Yeah,
Yeah.
because M of n is the sum of the Mobius values of all of the numbers less than n. It's not
Yes,
just
in
the
a very
divisors.
specific
So
serial.
while the sum over divisors is vanishing,
Yeah.
that's interesting, but it's not showing the Riemann hypothesis sum, which is the sum
Yes.
over
Yeah.
mu of k for all k less than n.
Mm-hmm. Yeah. I'm still trying to figure out what this slide is problematic. And I feel like even in our conversations with on Sundays, I haven't figured out the
It's
right
not
language.
problematic. It's a mistake. You have to open that up and try to
Yeah.
look at the difference between M of n and this sum over divisors.
Yeah. Yes. To be
Okay.
continued. This one is I left
I
a
mean, it's
mark.
very easy to make a jump and think that two things are the same, and then if they aren't, then you have to open it up and really look.
Yeah. I was thinking whether I should include this slide or not, but nah. I agree with you, Lou. I think it requires more attention. So I'm just gonna show you the final thing that came up. So we started with the set of primes 2, 3. Write the Pascal form or triangular form of the collection such in this way. So you just take 2, 3, and all the possible products of 2, 3 is 2.3. So you start with this set of size 2 or n, and you form the Pascal form. This is the collection of all square-free products generated by 2, 3. So now consider this method that I'm suggesting. So go back into this Pascal form and go to each of these entries and multiply each of the entries with the Pascal form of that entry. So 2 gets multiplied by itself 2, 3 gets multiplied by itself 3, 2.3 gets multiplied by 2, 3, 2.3. And if you follow this method, you're basically going to generate what I'm calling degree 2 numbers. So these are all of the numbers whose prime factorization, the highest degree is, you have to have a 2. And I define degree here. The highest degree prime in a number's prime factorization. So if you take a number, you break it up into its prime parts. The highest degree prime in that gives you the degree of that number. Then this should remind you of the degree of polynomials. That's kind of how we assign the definition degree to a polynomial. So for instance, the degree of 45, which is 3 squared dot 5, because the highest degree term is 2. So the degree of this whole number is 2. So here's the collection of degree 3 numbers. I use the same method. So I do 2, I go and I apply it twice, sorry. And I get this, which is the collection of all degree 3 numbers generated by 2, 3. And this is for 4. Apologize, it's like huge, but you see how simple it becomes. So if we were to replace every divisor in these collections with O for odd, and when the lambda is -1, because now we're working with the lambda function, not mu. Lambda has multiplicities. So that means that it's only the +1, -1 for lambda, if you remember. So so for degree 0, which is basically a fancy way of saying the number 1, has even has 0 factors, so we know lambda 1 equals +1. And degree 1, basically we're replacing O for E and E for O for -1 and E for +1 of lambda, and you can see how they basically cancel each other out. So E cancels out O, O cancels E, E cancels O, you're left with an O for degree 3. Degree 2, E cancels O, O cancels E, and you're left with E. And degree 1, E cancels O, O. So basically you'll see that degree 1 is odd, degree 2 is even, degree 3 is odd. And same thing with degree 4. These cancel each other out, these pairs, and you're left with the E. If we wish to sum the lambda values over these collection, and degrees 0 is simply E, degree 1 goes to O, degree 2 goes to E, degree 4 goes to O. Sorry, degree 4 goes to E, 5 goes to O, etc. If you try it out for on a big piece of paper, you'll see. So now we consider three primes now. Okay, so 2, 3, 5. Maybe it's going to look a little bit different. Maybe it's going to tell us something more. So the degree 1 collection is this, the Pascal form, which is the square-free numbers. And the degree 2 collection, you're going to each of these elements and you're multiplying it with their Pascal form. So this is what it looks like. So 2 is multiplied by 2, all the singles. Then the doubles are multiplied by the 2, 3, 2.3, 2, 5, 2.5, etc. And the triple is multiplied by itself. So if we were to replace these with just the lambda values, I could have done +1, -1, 2, but I just wanted something that was easier on the eye, so I chose O and E. And this, of course, degree 1 is basically the mu theorem that we saw, the Pascal's triangle. It's the exact same thing for lambda. Lambda and mu are the same if you're talking about square-free numbers. Degree 2, all of these are going to 0 for mu, but for lambda, we want to see what's happening here. But we see the exact same thing, so you can just notice that it's all in the Pascal triangular form. Like we're just continually placing it in the same form. So this is also going to push to a 0, as you can imagine. Okay, we have this, which is good. Maybe you can see. I just tried a lot of big thing here, but you can kind of see the patterns here that are emerging there, but they all basically cancel out to 0. For this whole collection, it's just going to cancel. It's just going to go to 1 O. Only 1 O is going to remain at the end. Everything cancels each other out. Just that one element. It's that Pascal triangle argument again, like that. When you alternate sum everything, it's going to go to that single one there. And those are the two theorems basically that the degree of the number, what I'm calling degree, which is just another way of talking about the polynomial degree, is in correlation with the Liouville function in this specific way. So this theorem, part A, is basically the same thing that we said in the previous section of the mu, that this is basically the Pascal triangle, and we use this Pascal triangle to show that degree 1, so degree 1 d1 is going to give you -1, is odd. Degree 2 is going to give you +1, which is even. So the degree 2 sum is always going to be even at the end, because in Pascal's triangle, that first column, that the surviving element is even. And for lambda, for d3, degree 3, it's going to be -1, etc. And yeah, I don't want to go into it now. I feel like I've overcrossed this time too long. I'm sorry. And this is basically saying it's the analogy of the argument used in theorem 1. And this one is proof for the second one, which I'm still working on, but I put my thoughts down here. And I'd rather we don't spend too much time on this because we want to talk about Appendix 9. And yeah, so this one is a reading that I came across, which is a little important too, that there's I.L. Sharon who published this in 2019. saying that Riemann's methods violate the law of identity, the law of excluded middle, and the law of non-contradiction of Aristotle. And Sharon also argues that the Riemann zeta function regularization technique employed by physicists introduces a contradiction whenever it is used. The thesis concludes with a non-conventional statement, namely that RH is a paradox and is thus not falsifiable. With regards to diversity of logics available to us today, Sharon has not found any discussion of the RH in the context of any of these logics. It appears that logicians do not apply logic to specific examples and that mathematicians lost interest in foundational questions after the development of Zermelo-Fraenkel set theory. And Sharon's thesis ends with a general observation that perhaps the mathematical community has not internalized the results of Gödel's work. And this is the last slide. So for the logician uninitiated in the apparent idiosyncratic treatment of convergence and divergence, the techniques of analytic continuation are invalid or paradoxical. Sharon's idea that RH is a paradox lends itself favorably to the mathematical and logical foundations of Spencer Brown's laws of form, which takes re-entry as fundamental. In the preface to the first American edition, Spencer Brown provides the following simple functional equation: x equals minus 1 over x, and that, like the analogous logical paradox, this statement is false. Functional equation is self-referential. The root value of x that we seek must be put back into the expression from which we seek it. Spencer Brown on page 11. Okay, so that's.
Can I ask a question?
Please.
Okay, my question is I have two questions that are related, but I'll keep them really short.
Okay.
Is the oscillating behavior of the complex I causing these lambda and Mobius functions to oscillate? And if so, or if not, what does this suggest about the atomic structureless building block nature of the prime numbers?
So the behavior of I and I don't know. Do you want to take this question, Lou?
Yeah. They aren't obviously related to one another.
Okay.
Oh, I missed the chat. Yes, the Sharon paper.
Also,
Graham, did I email it to you?
I would comment that Sharon's paper is interesting for its scholarship only.
Yes,
His opinions about the applications of logic are not really right.
Yeah, I was just reading that paper.
Also,
Whoa.
you might say that laws of form is based on paradox in the sense that it's based on considerations prior to logic. But it isn't as though you build systems that apparently don't have paradox on the basis of paradox.
Right.
That's a paradoxical way of looking at it.
Yes.
Okay, so now you've had a really good think about Spencer Brown's purported proof. How do you regard its status?
I think that feedback mechanism from the generalized Legendre formula needs to be understood better. And I mean numerically at first. I would like to understand how tightly it actually is working. He makes a lot of claims about it, but I haven't understood quite how to grasp it and take a look at it in more detail. Maybe you've thought about that.
Well, I have, but it's not trivial, is it?
No, not at all.
So,
And he just says it's good enough, which is great. He often gets a good insight and then gives it to you. You can investigate it.
what is? It's a great pity Jim's not here. What's Jim's latest position on this? Or his
Well,
current?
Jim will usually say that he's a scholar and he's
Yeah.
very careful to keep track of exactly what Spencer Brown said and what other people say.
Okay, I mean Spencer Brown told me you put a slide up there, Sahu, saying that Spencer Brown had a chat with Jim on, I think you said, was it the 12th the 8th of October 2012. Well, I had a fairly long discussion with him about 2 weeks later on exactly the same
Okay.
topic.
Yeah, I'm
But
curious.
it's a great pity Jim's not here. I'd love to
Yeah.
talk to Jim about this.
Another way of quoting Jim is Jim has been quoted as saying, "I read it 5 times and I found nothing wrong with it."
Yeah.
And
So
generally speaking, we have that experience in reading Spencer Brown. We don't find anything wrong with it.
Yeah.
But there are places where if such an assertion was true, then the theorem would go. But it's probably not wrong, but we can't prove it's wrong or right. Yeah, right.
Yeah. It's tricky. Before he went into care, I can't remember the year off the top of my head, but probably 2012, maybe 2000, probably 2013, when I went to visit him. I challenged him on some aspects of the proof. I can't remember what they were now. Probably something to do with the Denjoy hypothesis. I'm sorry, I just can't remember now. But he accepted at that time that it probably wasn't a proof. Now, I'm not sure. I mean, this is extremely uncharacteristic concession by him. So I wasn't quite sure whether he really thought that, or whether he was so frail at that time, because he was, I think this is when we were discussing arrangements for his 90th birthday, a possible commemoration for his 90th birthday. So he was pretty frail by that point. But he conceded that he didn't have a proof. But there we are.
There was a version that he had uploaded online to, and I think that the version that I was consulting is the 2015.
Yeah.
Just before he died, he might have passed in some final revisions to Thomas, I think.
Not that I'm possibly, I can't rule that out, but not that I'm aware of.
Because like there's slight difference in language in the 5th edition and the 6th edition. 5th edition, just very slight. But so we had to get our versions right as well,
right,
amongst the 3 of us, so we could talk about the same thing.
Yeah. The online edition, of course, the online claim preceded it by almost a decade. I think it was 2006 it went online.
Yeah, and I think that one was not correct. I think he had taken that one off.
Yes,
and
that's
then
right.
The second one, this is his second proof, the one that, but it's a totally different way of going about it.
Yeah, he took it down. Yeah. I've also got a question for Lou. Does someone else want to talk?
Yeah.
I was just going to say, is it only the analytic background which suggests the connections with quantum systems? That was my question.
Well, the original suggestion had to do with the distribution of zeros along the half-line, which looks like the zeros of a random matrix or random. So, I as far as I know, the relationships are mostly coming from the analytic side, but maybe there's more.
Intuitively, one would have thought so, but I don't know. Anyhow, please give my warmest regards to Jim when you talk to him.
Oh, sure.
Absolutely.
Doug?
Doug had a...
2 things. One is Shor's algorithm essentially is doing prime factoring using quantum Fourier transforms. So, and the algorithm, you have to be an analyst to even figure out what this algorithm means, even if you see the implementation. But essentially, you're using some mathematical theorem that says, given a guess for a prime number, using this quantum Fourier transform, it gives you a better guess, and then you can iterate through that, and it gives you the prime number. That is the factor of what looks like a prime number, but it's really the factor of 2 prime numbers. So that's what Shor's algorithm is. So it tells you there's a strong connection between quantum Fourier transform, specifically that algorithm, and quantum computing, because you can solve that problem exponentially.
That's true.
Quantum state. So So there is a strong connection between quantum theory and prime numbers. Example of that, and that's the killer app for quantum
Yeah,
computing.
that's a good way to ask the question. Is there a relationship between the combinatorics of the Riemann hypothesis and Shor's algorithm?
Yeah, exactly.
Yeah.
So anyhow, if you guys haven't already made that connection, I would say try to understand that algorithm, and if you need a particular link, I found a really good one that described it using that mathematical argument I just gave you, and I can send it to you.
Oh, send us the link. I'm always
Yes,
interested
yes.
in
Yeah,
descriptions of
so
Shor's
then
algorithm.
that's number one. So the other thing is you were talking about a balanced coin, a flip coin, you know. So is there anywhere in this work that you're doing that if you had a non-balanced coin, not that it wouldn't prove the Riemann hypothesis or not, but that physics would change as a result of some coin flip not being balanced anymore? And the reason I'm asking that question is because they know from PK experiments that random event generators can be influenced by the mind. So the question is, can you change physics by changing the normal distribution of things? And that's sort of the second question.
It'd be a skewed normal distribution if it was.
Right, but does it change physics per se? Sort of like the Bell statistics have an unusual statistics that you can't get classically. So therefore there's physics there that it points to. So is there another kind of physics that this might point to? That's the question for whoever can answer that.
I like that question.
That's what I believe is happening anyhow. So I'm just trying to look for more concrete evidence to support that argument.
Yeah.
Yeah, so I mean, random event generator stuff, they've done so many meta-analysis on it. Dean Radin has done it. So many people have done it. The Dean of Engineering at Princeton has done it, privately funded lab for 30 years, you know. There's more work than there that's done. Everybody's ignoring it. But it basically says the human mind can affect quantum statistics. Well, if that's true, then what does it mean is really the big question that I'm interested in is, well, what does it mean for what human thought is? Also, what does it mean for physics? What does it mean for entropy of closed systems? If all of a sudden the mind can reach into a quantum system that looks closed and change the probabilities of it. So there's with all that hoop around, there probably is a horse somewhere, you know?
Yeah, exactly. If it's unbalanced, there's in physics there would probably be a force, and I think the
change for sure, which has
you know, the force that is the biggest candidate has something to do with gravity. I keep trying to introduce that.
Yeah.
But
well,
how? I'm not sure.
Yeah, information is related to gravity too, but we don't know how a bit is related to, quote, a graviton, if there is such a thing. You know, how those things are related and how space-time emerges. All you have is bits at the bottom level, which is sort of Mike's and my premise. How does space-time emerge, and then how does gravity emerge from that? And so those are some of the things I talk about in my book too. But I don't have an answer, obviously, but nobody does. But at least some ways to look at it.
You Doug.
Anyhow, good talk. I learned things that I hadn't ever known about before. So thanks for that.
I mean, it honestly, it's all in Edwards and the original paper and all that. Like, you know, it just takes time to go through a lot of it. I don't know if I'm doing a good job, but it's just a lot of material, and it's been tricky to try to get the story straight, if that's even possible with this topic, you know. So I really appreciate the, you know, constantly being corrected also, like, hey, what you're doing is, it's not the right, okay, maybe you need to rewrite it, or that's not what you're saying, you know.
Pascal's triangle shows up as the number of unique terms, by the way, in geometric algebra. So this 1 plus A times 1 plus B plus 1 plus C times 1 plus D, that you can keep doing that, and the number of terms you get out of there is Pascal's triangle. So.
That's right.
Yes.
And if you put in for A, B, and C, prime 1, prime 2, prime 3, and so on, and expand it, you get all the different combinations.
I assume that you've read this this little book by Mark Kapp called Statistical Independence in Probability Analysis and Number Theory, where he has a chapter on primes play a game of chance.
Well, Peter, could you repeat the name of the book again, or the author?
Well, it's in the Karras Mathematical Monographs, number 6, I think.
Peter,
And it's called Statistical Independence in Probability Analysis and Number Theory. And it's by this well-known chap, Mark Kac, K-A-C.
Cats, yeah.
And he has a chapter in there saying, primes play a game of chance.
could you type that in the chat, Peter?
Hmm?
Could you type that in the chat?
Well, I haven't really managed to get on. I haven't really had time. But
Okay.
I haven't really managed to get onto the chat.
No,
But
the chat
send
in
you
this
the
session.
reference. I'll send you
Thank
the
you, Ben.
reference tomorrow.
All right. Okay. Thank you.
But he's very good because he just starts from Toynkossing and goes on to these more esoteric subjects as his ideas develop. But it was really quite interesting. But I thought you would almost certainly, since it's not an area I've looked into very much, and you the people who've been talking have clearly.
Thanks, Peter. I was not aware of that
deeply
one.
into things. Sorry, no, I missed that.
Is there a way to send things into this chat line?
Maybe uploading.
What files? No, Lou.
What?
No, I'm afraid not. You can't say.
Well, then I have to ask a question. I have been from time to time sending things to Anpa chat, but I'm not sure it goes correctly. Do you get spammed by me regularly in Anpa chat with papers and things? Just say yes or no.
Are you
I've
talking
had a bit of
to
spam
me,
from
Lou?
you, yeah.
I'm sorry. Was it a yes?
Yes.
It's a no from me.
No, from me.
Yeah. I mean, I've sent a lot of things, but I noticed the other day that they don't get sent to me, so I thought maybe it wasn't working.
They don't come to me, though.
Lou, the only thing that happens with yours is for some reason it thinks that it's spam. It does think it's spam.
But you get it.
I get it, yeah. But maybe that's
Okay,
my
because
spam.
I just got, okay, fine. I just got a copy of Mark Katz's book, and I'll put it in the Anpa chat line then.
Okay, all right.
It's 3 megs, so it's not a big one.
No, it's quite small. Yeah. Okay, so you've got it, Lou, anyway.
Yep.
I assumed you probably read it, but
No, I wasn't aware of this one.
because he's really because he quotes people like Erdős.
He's very good, very lively
Yeah,
mind.
yeah, he's a very nice way of putting things over. Anyway, you're obviously much more knowledgeable about this than I am. So
Graham, I'm very curious about your interaction with.
I'm going to have to go, by the way, because
Okay.
my wife's waiting for me.
Okay.
Thank you, Peter.
All the best. I'll see you tomorrow.
We'll see you tomorrow, yes, for your talk.
Yes.
got the honour.
I mean, I'm putting together a set of images, which I can then can I then display it? Can I then just you can put them in a file and then just display one image after the other. Is that I presume will be all right?
That will work, yeah. All right. Well, we'll look forward to your talk tomorrow, Peter.
Okay.
All right. Thank you.
Thank you, Peter.
Okay.
Are there any more
Bye.
questions? Bye-bye. Any more questions?
Goodbye.
I think
That was
goodbye is
wonderful.
not a question, but it's a statement.
Beautifully done. So,
Well, first of all, Sahu, thank you so much. That was, I can't say I understood very much, but that's my fault, not yours. and it's just, you know, I'm actually really pleased this week that, you know, new members of Anpa, new friends of Anpa are giving talks, and that's really hopeful for the future. So that's really good.
No,
Sahu, thank you. You know, I think it was interesting for people to fly over all that ground, because that's what you were doing. You were taking us up in a little plane and flying over all that ground from one end to the other.
yeah, thank you for those who managed to follow some or part of it. It's been really interesting working on it. And Graham, I would love for you to join our meetings too. You know, why not? Like, if you would like to come on Sunday, meet Jim.
Oh, yeah, we'd have to change our time, but we could do it.
Oh, right. You meet online. You don't meet physically, do you?
Oh, yeah, no, we don't meet physically. We meet online, but usually late. So.
Okay. I'd assume that you're all in Chicago.
Yes, we're in Chicago.
We are sequestered in Chicago.
Yeah. Okay. Okay. Well, Lou, drop me an email, or Sahu, drop me an email, and we'll work out a time, and I'll come. Yeah.
Yeah. See, we've been meeting at 8 o'clock at night. Now let's see. That for you is something like 2 in the morning.
Yeah.
So we could discuss between us a different meeting time.
Sure.
That would be like in a morning time, and then it would be available to you.
Sure. Okay. Let's do
After Anpa, we could do it at 11 o'clock in the morning.
that.
Yeah.
Okay.
Now that we know that this
There you go.
That's good for me.
There's also a small like laws of form seminar that we had been running for the last years, just very informal. So that will soon be revived. We're trying to do it on Fridays. So, but I'll let people know.
And that one meets at 5 o'clock in Chicago time.
Yeah.
Okay.
We're
Well,
looking at chapter.
a little
11.
late for me.
Thank you.
Okay, well, thank you ever so much, Sahu, and yeah, well, come and talk to us again, and I think, you know, this is really good.
Yeah. Great talk, Sahu. Great talk.
Tomorrow is the last day, so Peter's going to give us his talk, which it seems like a fitting end to this marathon that we've all been running, and then we're going to have our plenary, whatever that becomes, but I think 3 minutes is the limit. So think
3
minutes. 3 minutes. The mic goes on for 3 minutes, then it goes off. 3. Okay. There's a constraint for you, and it may be that you're asked to do things. It may be you're asked to draw things, or I don't know. I don't know what people have got planned, but come prepared, and we'll just see how it goes.
Great.
We'll all be so knackered we won't care anyway.
Or be sure to record this 3-minute marathon.
Yeah, absolutely. Okay, so we'll see you tomorrow.
Right.
And for the last meeting. Great. Okay.
Bye.
All right. Bye-bye.
Bye.